So in continuation with my previous session where I talked about inter-process communication, which largely kind of dealt about how services are likely to communicate and what's the different patterns across sync and async. Now we're at a point where the services will kind of talk to one or more services to achieve a specific business outcome. Now, as a part of the business outcomes, these business transactions kind of span across multiple services, and with each transaction, there's a fair chance about which kind of comes back into consideration is for every commit of a transaction, there's a rollback. So that's kind of gets into an arena where we need to manage transactions a little differently, and the transaction get a little bit more complicated when the entities involved in the transactions are of different nature. They could be writing to a database, sending a message to a queue, at the same time calling another service. So all of this actually have to run across a transaction, and either of the entities in the transaction which kind of fail, then that's where the rollback kind of comes into play. Now, distributed transaction, typically, if you really look at microservices, there will be a need to implement transactions that span multiple services. Transactions are kind of core to enterprise business. Asset transactions simplify the job of developer by providing an illusion that each transaction has an exclusive access to data. The emphasis I need to kind of lay out here, illusion and exclusive access to data. So if you look at most databases, which you've worked in the last 2-3 decades, SQL and Oracle generally play a lot with various isolation levels, everything being from 0 to 4, all the way being highly serialized by nature. But obviously that's going to screw up the performance. Now, taking Q or intuition from asset transactions, trying to implement similar into microservices, there are challenges. And what's the different patterns which really come into play, which I'm going to talk to in a minute. Now, before kind of getting into solving the problem, how to implement ACID in microservice transactions, now the idea really kind of comes to the point of discussion is, okay, there has been distributed transactions for last 2 to 3 decades, which you've been seeing in most databases. Why is that not a good option for microservices? Now, it turns out that SQL, Oracle, and most of the databases are XA compliant. Now, OpenXA is a standard which kind of helps transactions to be managed across distributed entity, and that's how kind of gives the idea of distributed transactions. Now, most SQL databases and some message brokers are XA compliant. Modern tech, however, NoSQL databases, message brokers like RabbitMQ and Kafka are not XA compliant. So that kind of gives rise to a problem. Of course, distributed transaction requires a synchronous IPC, which kind of reduces availability. That's one of the reasons which, going down that path doesn't really work. Now, microservices have single databases per service. Now, business transactions that span multiple services need a mechanism to implement transactions that span services. So you implement each business transaction that span multiple services, essentially what we call as a Saga. Now, Saga is nothing too complicated, the sequence of local transactions. Now, each local transaction updates the database, publishes the message or event or to trigger the next local transaction in Saga. In case of failure, local transaction Saga performs a series of compensating transactions that undo the changes that were made by preceding local transactions. Now, the system operation initiates the first step in the Saga. The completion of the local transaction triggers the execution of the next local transaction. Coordinating of these steps are implemented using asynchronous messaging, which ensures all the steps in the Saga are executed even if one or more participants are temporarily unavailable. So typically, when you're talking to multiple services, there is a chance that one or two services may not be agreed. May not be available. So, the coordination really has to handle. The Saga differs from ACID transaction. They really lack the isolation property. We'll talk to in a minute in terms of how to deal with isolation. Now, each local transaction commits its changes. A Saga is rolled back using compensating transaction. Now, this is an example of a Saga pattern where you can see the order service, the consumer, the kitchen service, and accounting service. There's a series of steps which has to perform, and then eventually that's how. But yeah, the challenges of a Saga pattern typically is lack of isolation and challenge of rollback. Now, compensating transaction, I just want to take a minute to kind of walk to going back to the same conversation around a database. You have an insert, update, delete, all of it need to be performed as a part of transactions. And if the transaction were failed, then you issue a rollback command, and that kind of takes care of everything. But apparently, what really happens in the rollback? So let's say you're doing transaction T1 to Tn. Now you fail at Tn plus 1, and eventually the compensating transaction has to undo in a reverse order from Cn to C1. So that's how the sequence of steps from is T1 to Tn and then Cn to C1. So Saga executes a compensating transaction in reverse order, or the forward transaction Cn to Ci. So as you can see, there's a lot of coordination effort which goes into the Saga in terms of sequencing the execution, forward and compensating transaction. It's a whole lot. And this thing gets a lot more complicated when you're dealing with fairly heavy microservices architecture, which can end up being very, very complicated. Of course, so you can understand that you can come around to understand the complexity in the coordination logic of Saga is where the problem is, and there are various solutions to it. So coordinating Sagas. Now, if you really look at consists of logic which coordinates the steps in Saga, happy flow. Coordination logic selects the first step in the Saga, executes a local transaction, completion of the local transaction, Saga sequencing coordination selects and invokes the next Saga and participant. Participant process continues till the Saga completes all the steps. If there's an exception, Saga will go ahead and compensate, will be executing the compensating transaction in the reverse order. Now, kind of focusing on the coordination piece, there are two different types of patterns or structures which come into play. One is choreography. Just from the very name and the meaning of the word, it basically just distributes the decision making and sequencing among Saga participants. So it's a typical pops up scenario where, going back to the Starbucks example, the order creation service creates an order, sends out, I have created the order number so and so into the universe, and whichever services are interested in that will then eventually, whoever subscribed for it will kind of make use of that. And whatever has to happen beyond that is nothing to do with the order service. Primarily, they communicate using exchanging events. On the other hand, orchestration is a lot different. It's basically centralized Saga coordination logic in a Saga orchestrator class. A Saga orchestrator sends command message to Saga participant telling which operations to perform. Furthermore, kind of getting into choreography-based Saga. And now Saga participants subscribe to each other's events and respond accordingly. Taking an order creation example for Starbucks, the happy part is you place an order to the cashier, marks a coffee cup with your order placed in the queue. Queue is literally a queue of coffee cup lined up in an espresso machine. Decouples the cashier and allows the cashier to keep taking orders. This allows to deploy multiple barista in a competing consumer scenario. Order gets picked up by a specific barista, and order gets serviced by a barista, and order is moved to the customer bay for pickup. So you see that Starbucks is a heavily asynchronous architecture. So participants in the choreography-based Saga interact using PubSub model. So I just published the event, the order's been created, and everything has to happen as a magic. Exception scenarios are there, which again things get a little more complicated. You deliver incorrect drink or a machine breaks down. What are the actions you take? Similarly, in case you refund the money, and common error handling strategies include write-off, retry, and compensating. Now, turns out there are some drawbacks and benefits of choreography. So, but before kind of getting, there are certain two things which you need to keep in mind for choreography. So choreography typically talks a lot of transaction messaging. What it ideally means, a Saga participant has to update a database and publish an event as a part of the database transaction. For example, order creation. The previous example includes created an order and sending as an event to the queue service that a new order has been created. It's important that the database update the publishing events happen automatically. So this is where the transactional messaging really comes into key. Mapping. It's another important area where typically, going back to the Starbucks example, in the whole choreography universe, you've kind of pushed out an order, and now the order has to kind of come back to you in terms for cancellation. So how do you really kind of get around knowing what is what? So there has to be a correlation ID which you send off as a part of when the order creation has been done, which comes back to you with the performance, with the action which needs to be performed in terms of cancellation of order. So this is a there has to be some kind of tracking mechanism. Coming down to benefits and drawback, as you can see, it's simplicity. Services publish events and they create, update, and delete business objects. Loose couple participants subscribes to events and don't have direct knowledge to each other. Drawbacks makes it difficult to understand because we really can't understand the thing. By single piece of code, an orchestrator would actually tell you how the whole thing works. But in case of choreography, since all the logic is kind of been residing somewhere else from a decision-making standpoint of view, the high chances trying to read that code can be really, really complicated affair. Cyclic dependencies are very often created in situations like if you're not designing the system well. Risk of tight coupling, each Saga participant needs to subscribe to all the events. So that's another area. Furthermore, now kind of getting into orchestration-based Saga. The orchestration-based Saga, the sole responsibility is to tell the Saga participant what to do. Saga orchestrator communicates with the participant using command async style interaction. To execute the Saga step, it sends a command message to the Saga participant telling what operations to perform. After the participant that has performed that step, it sends a reply message to the orchestrator. Orchestrator then processes the message and determines which Saga steps to perform next. So you can see it turns out the orchestrator is the central, conductor orchestrator in the entire thing. Implementation specific model. So you ideally end up modeling orchestration-based Saga state machines and use a transactional message to ensure reliable communication between Saga orchestrator and participant. This is an example of Starbucks, which talk about create order, using transaction. Of course, I share the PowerPoint presentation. You can go into depth, fairly simple, not too complicated. Modeling of Sagas orchestrating a state machine. State machines consist of a set of states. Transition between states are triggered by events. Each transition can have an action, which a Saga is an invocation of a Saga participant. Transition between states are triggered by completion of a local transaction performed by a Saga participant. Correct state and specific outcome, the local transaction determine the state transition and what action. State machines provide an effective strategy of designing, implementing, and testing Saga much more easier. So you could probably pivot to, when you get to the designing piece in terms of how the communication, how the interaction between services really have to go, that's where, state machines play a major role. Of course, there are drawbacks of orchestration-based Saga as well. So, and benefits. Simpler dependencies do not introduce cyclic. It's easy to handle cyclic dependencies when you know that orchestrator, because you're writing the code and the unseen is often seen out here. So the chance of you getting to cyclic dependency is pretty rare. Less coupling. Each service API is invoked by the orchestrator, so it does not need to know about the event published by the Saga. Improves separation of concern and simplifies business logic. And the coordination logic is localized to the Saga orchestrator. Domain objects are simpler and have no knowledge of the Saga that participant. Drawback. Risk of centralizing too much business logic. This results in a design where the smart orchestrator tells the dumb service what to do. This can be avoided by solely using orchestrator for sequencing. So that's, again, there are ways and mechanisms in terms of how you kind of do away with the drawback. Now, coming down to a more important area in terms of isolation. So I in isolation property of ACID transaction ensures that the outcome of execution multiple transaction concurrently is the same as they were going to do it in a serial order. So databases provide an illusion for each ACID transaction has exclusive access to data. Isolation makes it a lot easier to write business logic that executes concurrently. Now, Saga lacks isolation. That is because updates made by each of a Saga's local transaction are immediately visible to other Sagas, and once a transaction commits, causing two problems. Other Sagas can change the access data by the Saga while it's executing because it's still in the process. It's not kind of completed. That leads to dirty reads. Any Saga can read the data before the Saga is completed. Its updates consequently can be exposed to an inconsistent state. So these are very obvious problem when it comes to isolation, and that's being dealt with databases. Sagas are ACD, so they support atomicity, ensures all transactions executed, all changes can be undone. Consistency, RI within the service is handled by local database. RI across services are handled by services. Durability, handled by local database. Lack of isolation potentially causes what the database literature call it anomalies. Anomalies when a transaction reads and writes data in a way that wouldn't if the transaction was executed one at a time. When anomaly occurs, the outcome of executing Saga concurrently is different and than it were executed serially. Now, before kind of getting a little deeper, first let's take a quick recap on 1 minute.